Tēnā koutou, ngā mihi nui ki a koutou katoa, ko Glen Rowe, toko ingoa. A very warm welcome to you all. My name is Glen Rowe, and it is my pleasure to introduce this presentation, which is part of a series of talks for the 2020 RASNZ online conference. Rene Breton, Professor of Astrophysics at Manchester University, was going to be one of our invited speakers at this year's in-person conference. Rene has kindly given permission for us to use a talk he presented to the Royal Astronomical Society, London. In the presentation, Rene discusses the achievements of the last 50 years in using pulsars to test Einstein's theory of general relativity and describes some of the strange behaviours of space and time when submitted to extreme gravity.
So it gives me great pleasure to present Dr. Breton, who will be talking to us about Einstein's relativity. Thank you.
All right. Good afternoon, everyone. Thanks for coming in such a great turnout today. So I work at the Jodrell Bank Centre for Astrophysics in Manchester. I spend some of my time working at the observatory, and the rest I work at the university. And my area of research is about pulsars, so the really extreme objects, as you'll learn today. And we can actually use them, among other things, to study gravity and test Einstein's theory. So it's been just over 100 years, actually, since we got General Relativity published. And since then, we made a lot of progress understanding it and testing it. And part of it is thanks to pulsars. So in today's lecture, there'll be three sort of topics. The first one is that I'm going to give you a very brief introduction to what pulsars are. Then we'll talk about relativity. And basically, in the last segment, we'll put the two together and see how we can use pulsars to test relativity. So I hope you won't be too mesmerized by the end. Obviously, relativity is not an easy topic, but I'm hoping that at least I can give some examples that you might be able to grasp, on sort of like hands-on phenomena related to relativity. All right, so first round on pulsars. So what are pulsars? Pulsars are these very tiny stars. We're talking about objects something like 10 kilometers in radius, so sort of like central London type of size. But they're a very dense object due to the fact that they contain a lot of matter. So in a typical pulsar, you would find about 1.5 times the entire mass of the sun, all scrunched into that tiny ball the size of London. And so if you were to look at the average density of a pulsar, it would be comparable to taking every human being on this planet and shrinking them all, squeezing all of us living on Earth down to the size of a sugar cube. Okay? So if you're able to do that, you would have roughly the same density as a pulsar. Okay? So extremely dense objects. And they're also highly magnetized. So they have a magnetic field, a bit like the Earth. So there's a North Pole and a South Pole, except that their magnetic fields are way larger than the ones we're used to. We're talking about 10,000 billion times stronger magnets than the Earth. Okay? So if you go around the pulsar, I suggest you don't bring any keys or spare change, as otherwise you might get stuck flat out onto the surface. They also spin very fast. So their spins range from a couple of milliseconds for one rotation to about 10 or so seconds for the slowest ones we observe. Actually, just this past summer, a student in Manchester discovered the slowest one known at 23.5 seconds. So it's rather long compared to some of the other ones. So the fastest ones, they spin much faster than, say, your kitchen blender. And if you're a Formula One amateur, you should probably know that the typical RPM on Formula One cars is something like 30 or 40,000 RPM, or even less. And so pulsars actually spin faster even than Formula One engines. So the object itself, we call them neutron stars. So that's the type of astronomical objects they are, bearing to the fact that they're made up mostly of neutrons. And the ones that we call pulsar, we call them this way due to the simple phenomenological fact that they blink. And they blink because the light that they produce is actually emitted along a narrow beam of light. So they're not, it's not emitted in all directions, but in a beamed way. And so just like a lighthouse by the seaside, you will see the pulsar being bright only when that cone sweeps across your line of sight, which then makes it blink every rotation that the star is making. And so the name came after what's been observed, pulsar for pulsating star, as they are known. And so this is what you typically observe for these objects, just a little blink. Most of them are actually visible only in radio light. So you need special telescopes, not the ones you use to look with your eyes, but the light that's emitted at radio waves, which is also a type of light. And radio waves, we're all familiar. That's what we use for mobile phones, to listen to the radio. So that's the same types of frequencies that are being used to detect these objects. Today we know of about, well, that number I should update because it grows sort of like almost every day or every month. So we know just over 2,600 pulsars. And the way they appear in space is actually from the death of massive stars. So as you may know, stars don't live forever. Small stars will live longer. And the big stars, they live on a shorter time span. And the big stars, at the end of their lives, they will explode into what we call supernovae. And these exploding stars don't actually make the entire star fly apart, but the core of the star typically remains there and actually shrink because there's no power source to keep them from falling into a very compact object. So the massive stars, they're the ones who turn into black holes, but also some of the massive stars, actually the vast majority of massive stars, actually turn into neutron stars, which might become pulsars. So on this image here of a very famous nebula, so a big cloud of gas that's floating in space, this one is called M1, Messier number 1, was discovered by Charles Messier. And you can observe with a small amateur telescope. So this one is the remnant of one of these supernovae that exploded in 1054 of our era, so about 1,000 years ago. And if you look at images of this little cloud, over time you will see that actually it expands at a rate which is consistent with the fact that 1,000 years ago, all this gas was into one clump at the center, which actually fits with observations of Chinese astronomers who did see that star exploding. And so now what's left behind is this nice cloud, but at the very center, near the place where it's a bit saturated right there, there are two stars, and most of the points there, actually all the points are either foreground or background stars, but one of those two stars right there is actually sitting right at the center of this expanding cloud, and it turns out to be a pulsar. And so that pulsar, we call it the crab pulsar, because that nebula is commonly referred to as the Crab Nebula. So that one was found in 1968, the blinking star, but the first pulsar was found a year earlier, in 1967. Jocelyn Bell was a graduate student back in the days at Cambridge and was the one who discovered the first of these pulsars. If you were to look at a pulsar with a telescope, like the Lovell telescope at Jodrell Bank, you would see something that looks like what's going to be traced on the image at the bottom. But also, if you were to essentially plug in the telescope to a big amplifier and then to sound speakers, you could actually hear the pulsar. And so let's just see what it might sound like. So this pulsar is one of the most famous pulsars. We call it B0329 plus 54. That's basically the postcode to where to find it in the sky. And it's a rather slow pulsar. So the interval between them is about 0.7 seconds. And you can see that the intensity varies because of various phenomena, intrinsic and also extrinsic to the pulsar. So each pulsar basically has its own fingerprint, like the sort of pulsation, the image that they leave is different from one to the other. So it's really unique to each of them. Some will have like a single one, some will have multiple ones that can be narrow or sometimes broader. And so you know, for the astronomers, actually, you know, sometimes you can look at one and say, oh yeah, that one is, you know, this pulsar, because we're geeks and we sort of like remember what they look like. So that's the same I just played. Here's another one. So this one is called 0437. It's 5.5 millisecond. So you can't hear each blink. For this one, it's too fast. Then the crab pulsar is this one. So 33 rotations per second for this one. So you can just about hear each one of them. Then Vela is a bit slower. I like this one. It feels like if you didn't know it was a pulsar, you could think it's a Western movie, right, with the person on a horse. And then this one, 1937, used to be the fastest known, was discovered in 1981, and it was the fastest known for about 25 years. And that's how it sounds. So it's not very pleasant to listen to. So you may understand that we usually look at the imprints rather than listening to them, because otherwise, you know, I'm not sure I could be sane after a couple of hours. Some of the pulsars are actually in binary systems. About 10% of them have a little star orbiting around them. And typically, when they're in binary system, they experience something that we call recycling. So basically, the bigger star, in terms of mass, is the one that evolves faster and becomes a giant star at the end of its life and then explodes. So we'll just see that in a second. So it explodes and turns into one of these neutron stars that may blink. So you have a little pulsar. Eventually, the companion star will also evolve. And if they're close enough, when it becomes big, it might start actually transferring mass onto the pulsar, owing to the large gravitational pull of the pulsar, which then drains some of the mass. But when that mass falls onto the pulsar, you might have noticed the pulsar actually goes and spins faster. And so it's a known phenomenon of conservation of what we call angular momentum. So the idea is a bit like in a merry-go-round in a park. So I'm sure you've all played, you know, on one of them when you were a kid, or maybe still now. You know, if you're on your own, you push it, then you hop on, and then you spin, but eventually you slow down, and then, you know, it gets boring. So that's what a regular isolated pulsar experiences. But then if you have a pulsar that's got a little friend, then basically when it dumps matter onto the surface, it's just as if like friends were, you know, running and then jumping on board. So then it gives a little kick every time. And that's how they can end up spinning so fast. And like I said, in some cases, they can do hundreds of rotations per second. Okay, so that's the end of like the pulsar part, properly speaking. So now you're kind of like, you know, expert, you know, pulsar expert and, you know, Pulsar 101 kind of a crash course. Now let's move on to relativity. Okay, so that's the easy part of the talk. So actually, relativity was, well, you know, came up with this grimacing guy, Einstein, at the start of the 20th century. But relativity, what you may not know is that it's actually two theories. So the first one came in 1905, and we call it the Special Relativity, because it's considering a scope that is limited, whereby basically it deals only with objects in our universe that are either not moving or moving at a speed which is constant. So in principle, it cannot explain the behavior of objects going near other objects, so like in a gravitational field, and it cannot explain what happens if things are accelerating or decelerating. So it was a very particular scope. And this theory actually came up, like you can derive the entire, if you're really clever, so which, this guy was, and then I did learn how to do it, but, I could not come up with it in the first place. You can come up with this theory with only two principles. The first one is that speed of light is constant, and the other one basically says, and that's the principle of relativity, that the laws of physics should just be the same for anyone in the universe, regardless where you're located. And just with this, you can derive the entire theory. And some of the main consequences, and that's what I think is most important for you to perhaps understand today, is the consequences like mass energy being equivalent. So this is this famous equation, basically E equals mc squared, that you see people wearing on T-shirt when they go to the beach. So, it's very famous, but people don't quite know what it stands for, right? So especially at the beach. This basically tells you that energy and mass are equivalent, so they're interchangeable. So if you want to describe the behavior of an object, you can you can basically consider the mass of the object, and that would tell you how the object should move. But also, if the object, let's say, had no mass, and it was just a bundle of energy, you could also describe its motion. And a bundle of energy, well, does exist, actually. They're called photons. So photons are particles of light. And particles of light actually don't have any mass. So you cannot take light and just kind of like stop it and put it on a scale and weigh it. It's impossible. So light actually only has a sort of analog to a mass due to the energy that they carry around. And so if you want to explain how light moves around space, you basically need this equation to be able to relate things to how a cannonball, by extension, would also be behaving. Okay? The second principle is really interesting. We call it the composition of velocities. So let's consider this little thought experiment. And Einstein was very famous for doing these little experiments in his head. He would, kind of like speculate what would happen if I was able to ride a photon. How would universe, look to me? And so our experiment today is basically about a train. Okay, I took the train from Manchester today, so that that was quite good. And then people, practicing, I don't know, like archery for whatever reason. And so imagine you have the target, and then you have someone standing on the ground and, shooting at the target. And let's say that their particular device, the bow, is actually able to, send the arrows at 200 kilometers an hour, okay? And then that person basically, has a friend who bought the exact same equipment, okay? So that arrow from the train window, okay? So don't try, because I'm pretty sure they'll kick you out of the train. But if you were able to open the window and throw your arrow, the arrow would also travel at 200 kilometers an hour. Now, let's say the train is a fast one, so it goes at 100 kilometers an hour, because we all know trains are usually much slower than that. So what would be the speed for the arrow at the target from the person on the ground? It would be 200 kilometers an hour. What would be the speed recorded for the person on the train shooting the arrow? So 300 kilometers an hour, right? So one speed plus the other one. Now, if we do the experiment again, but instead of using arrows, we use light, okay? So the person on the ground will shoot light at the target. Now I'm not sure what sort of contraption this is, but it could just be a laser pointer, okay? Then shining light at the target, okay? So the light would reach the target at the speed of light, which in actual numbers is something close to 300,000 kilometers per hour. Okay? Per second, sorry. Yeah, thank you. Yeah, that was a test. Okay, so now, if the person on the train was to do the same, so shooting light at the speed of light and traveling at a rather fast train, which also goes at the speed of light, okay? What speed would light come to the target? So you all say c, so speed of light. But just like less than 5 minutes ago, you told me 200 plus 100 is 300. And now you say 300,000 kilometers per second plus 300,000 kilometers per second is 300,000 kilometers per second. Okay, so something doesn't work here, right? And it's because you paid attention, and basically you noticed that before I said that the speed of light is constant, and that it should be true anywhere in our universe. So there's a little trick here that happens is when you actually calculate velocities of stuff that move in our universe, adding velocities is actually something that's actually wrong. It's just that if you go at a very low speed, things seem to just add up, you know, the way we intuitively think. But as you go closer and closer to the speed of light, or at the speed of light, then this rule of adding things doesn't work anymore. Sorry. And so you need to use another formula, which is beyond the scope of our lecture today. Okay? And so you're limited, basically, to reach, you know, the speed of light at best. Okay? And so this is very curious, but it explains a lot of things in our universe. And one of them, for instance, is also that time and lengths in space are not something that is constant. So your perception of time might be different from the perception of time of something moving at really high speed. So the faster you move, in fact, the slower your perception of time is. Okay? And it's all consistent. So basically, if you have a twin, okay, you stay on Earth and you send your twin traveling at nearly the speed of light, and your twin comes back, you know, in 40 years from now, your twin will come back and will still be like a, you know, young teenager or something, and you will have aged 40 years in the meantime. Okay? And it doesn't break any laws of physics. So it's very, very strange. Okay. Then it took another 10 years of hard work to Einstein to then come up with the second theory, the theory of general relativity. And so as the name hints, this one has a broader scope, and it actually includes describing how objects behave in the presence of a gravitational field. So how planets, for instance, orbit around the sun. And it deals also with things that accelerate. And the main sort of point of this theory is that space-time, basically it tells how matter should move, but then matter tells how space-time should behave. And you'll see the illustration in just the next slide. But before we get there, so this is Einstein's theory of general relativity. Okay? So if you're really cool, so after this talk, you'll go and get a T-shirt made for the beach, but you'll put this equation on instead. Okay? So that's, you know, that's the fully trained, you know, physicist version. Okay? And so this equation, again, equations is a balance, right? So it tells on one side, so we won't get into all the maths, but on one side, it's space-time, basically, and space-time is equivalent to what is the content of the universe, so mass and energy that lies within space-time. And so we'll see some illustrations of that. For instance, space-time can be warped and light can be bent. Okay, so space-time is like this fabric containing the 3 dimensions we're used to, spatial dimensions, and also time as an extra dimension. And we used to think of time as something, you know, very different from lengths. But in terms of calculating quantities, they're all essentially the same. It doesn't matter if you're talking about time or lengths. And so one of the consequences, basically, if you have mass somewhere, so let's say you have the sun, then space-time will actually be curved around the location of the sun. Okay? And so this means that, you know, if light comes from a far away star, it will travel in a straight path to you, but then as it comes close to Earth, passing, say, near the sun, it would follow the natural curvature of space-time on its way to you. So it's just a bit like, you know, if you go to the casino and you play, you know, the roulette game, you know, you toss a little marble and then it just spins around in the curved space. And if you give just the right, you know, push at the start and there was no friction, then that little marble would just go around in a circle in the bowl, right? And so that marble will essentially be kind of in orbit around the center. So planets that orbit stars, they're just basically going around this like bowl-shaped space-time, and they just go around in straight line, but on this curved space-time, basically. And if you have anything else, like, you know, a light from a star coming from far away, or I don't know, some comet coming from very far, as they plunge towards the center of the solar system, they just get deflected as they follow this natural shape, okay? So general relativity, that's basically it, really. It's just curving space-time, and the amount of curvature depends on how massive the object is, okay? Now, I would agree that in practice, it's a bit more complicated when you look into the equations, but conceptually, that's basically it, really. One of the really amazing consequences is that if you accelerate, you can basically mimic the effect of gravity, and you could actually not even tell them apart, okay? So if you go into space, like, you know, a week or two ago, Tesla, you know, sent that, like, you know, car going to Mars, right? Now, the car is going at pretty much constant speed to Mars. So, you know, basically the little mannequin is sort of like floating around. I guess there's a seatbelt keeping it there. But, you know, it's kind of floating, okay? But then if all of a sudden there were, like, you know, little motors and basically pushing, you know, the car to accelerate, if that car could accelerate to reach 9.8 meters per second square of acceleration, the person in the car would feel just like if they were on Earth, okay? Because that's the gravitational acceleration. So if you drop an apple, it accelerates, and that's the rate of acceleration, which is due to the gravitational field on Earth. So going into space and accelerating in a space capsule or being on Earth is actually no different in terms of laws of physics, as long as the net acceleration is the same, okay? So it's very strange because, I mean, you know, you could trick your friends, put them in some sort of like space capsules, send them away, and they would not even notice, right? So, yeah. Okay, so that's what we need to know about relativity and also about pulsars. Enough at least to kind of understand how we can test relativity using pulsars. So the first question we need to address is, why do we use pulsars? Why are they interesting? And actually, we use only certain types of pulsars, the one in binary system, when we want to test gravity. The first reason is that they're very precise timing, so they're good clocks, okay? So, and we talked about that essentially in the first part, right? They tick-tock at regular interval, and actually the interval at which they tick-tock is really accurate. It doesn't change over time. In some cases, and that's one of the best ones, this particular pulsar, we can measure the arrival time of each pulse to about tens of nanoseconds. Okay, that's accurate. We can tell when it's going to come. Okay, and on a certain date, so let's say June 16th, 2014, at 8:10 a.m. Okay, at that very particular time, the pulsar spin period was 4.5701, and then we go something like 4, 8, 12, something like 15 decimal place. Okay, and that's how well we could measure the rotational period of that pulsar. Okay, so it's just fabulous. But also it's very steady over time. It will slow down, but you can predict exactly how it will slow down. So if you were to observe it like today, you could predict exactly what the period would be, and you could tell exactly to the nearest tenth of nanosecond or tens of nanosecond or so when the next talk would take place. Okay, so they're amazing clocks, pretty much on long time scale as good, if not better, than atomic clocks, which we use as time standards on Earth. The second amazing properties of pulsars is that they're very compact objects. So why is there a picture of a beach here? Is because, well, I wish it was sunny like this, but also because, if you go to the beach, obviously, there are tides, right? So water level goes up and down twice a day. And this is because of the gravitational pull of the moon and also the sun, okay, which basically makes the Earth look a bit oblate. It looks a bit elongated in the direction of the moon and also of the sun. So pulsars are so compact, they're so dense, that if you put like a pulsar in place of Earth, the moon will have absolutely no effect into deforming the shape of a pulsar. Okay? In fact, you could take two pulsars, put one at Earth, and put the other one at the moon location, and even though they're quite close and very big, very massive, they will still look perfectly spherical. Okay? And this simplifies a lot of things, because if you try to calculate the motion, if you have something like a fluid and something not too dense like Earth, it becomes very messy calculating the trajectories. So we can do it for Earth, but there's lots of corrections and it's a bit cumbersome. So for pulsars, it's a very clean kind of like textbook, ideal case. And so we can go and look at pulsars and we can monitor their orbital motion to a really high accuracy. And the way we do it is using a very simple phenomenon, which we know as the Doppler effect, or as the French like to say, the Fizeau effect, because Fizeau also independently discovered this effect. The idea is the same as, let's take a train coming towards you. Then the train has a high pitch, right? High frequency. Once it passes you and goes away, then the tone goes to a lower frequency, right? And so this is the Doppler effect. So basically, the frequency of light is higher frequency than at rest if the object comes towards you. So it's like for like an ambulance, and then once it's going away, it's like so that sort of thing, okay? And that you can see in a pulsar as well. If the pulsar comes towards you, then the tick-tock will be a bit closer from one another. The frequency of the tick-tock will increase. And then if the pulsar goes away from you, then the interval between them will spread. Okay? So if it's in a binary system, then for kind of like half the orbit, it will come towards you. And then for like the other half, it will go away from you. And so you can just monitor the signal very carefully, and you'll be able to see this sort of cyclic pattern in the frequency of the pulsar. And using this, you can basically tell exactly how long it takes for one orbit, and you can map the exact trajectory around the other object. So that's how we measure the orbit of pulsars. The same phenomenon is what we use to tell that distant galaxies are going away from us. We call it the redshift. So it's the same physics, basically. Okay, so what happens if you put a pulsar and you give it a very heavy companion and you put it in close proximity? So let's say you put a pulsar next to another neutron star. The other one might blink. Maybe it doesn't. Maybe you don't see it blinking, but it's enough to have just one object about which the pulsar orbits to then see this cyclic change in the pulsation. So what happens when you do that is if you try to calculate the orbit and you use Newton's laws of physics, it won't explain very well the orbital motion. It will break down. And again, this is kind of like the same idea as earlier about adding velocities together, right? So if you don't move very fast, the sort of intuitive laws work. So for orbital motion, it's Newton's law. So kind of like what explains, cannonball motion. It works really well if things don't move very fast. So we can explain, for instance, the orbit of the Earth around the sun to really great accuracy just using Newton's law. But if you take two pulsars, then it will not work very well. And so this is what Einstein's theory is there for. It's the extension for the more extreme limit. And so let me just example that with this sort of poster child, which we call the Double Pulsar. So it was found by colleagues of mine based at Manchester and also elsewhere in the world in 2003. So they first found this new pulsar, which spins at 23 milliseconds. So they could see it blinking, and they knew there was an invisible object around which it was orbiting. But then, within the next couple of months of observing it, they noticed actually that the other object was also blinking, and both of them have exactly the same orbital period. So we know that, the other one you see blinking is actually the companion to that first observed pulsar. The second one is fainter, so that's partly why it took longer to be detected, and it's found to blink at 2.8 seconds. The two of them orbit in only 2.4 hours, okay, for one orbit, and their distance is roughly the same as the Earth-Moon distance, okay? So Earth-Moon, the orbit is about 27 days for one revolution around. But here, because the masses are so large, they zip around in only 2.4 hours. Okay? So you can imagine the sort of like speed at which they must be orbiting. And this is why these effects of relativity are so important. So one thing you notice is the orbit is actually elongated. We call it an ellipse. And actually, the ellipse normally should just like stay the same over time. But what you see in these systems is that the ellipse drift over time, okay, does this sort of like spirograph, motion. So we call it precession. And actually, it does apply to orbits of, planets around the sun, but it's so tiny that it's kind of negligible. Actually, the one for which it's largest is our planet Mercury, and because it's the nearest to the sun. And Le Verrier is the one who discovered this anomaly in the orbit in 1859. But the drift, the angle between one and the next one cumulated over 100 years is less than a degree of change. Okay, so it's really, really tiny. If you look at that double pulsar system that we found, it's 17 degrees per single year, the drift. Okay, so in 21 years, the orbit will have done a full cycle of precession and will come back to the original orientation. And this you can only explain using Einstein's theory, basically. So Einstein himself had managed to explain it for Mercury in 1915, and now it's been observed elsewhere. Something else that takes place in binary systems is that they will go and get closer and closer over time due to the fact that as the bodies orbit, they emit gravitational waves. So as objects move in space, they create little wavelets in space-time, and this propagates a bit like if you throw a rock in water, you create these wavelets, and then it just spreads out. And this carries energy, and the energy comes from the orbit, so they shrink over time. So eventually, binary systems, like the double pulsar system, will shrink and come into contact and merge and turn into a black hole. So this is what was observed last August of this past year, and was announced in October. LIGO, the detector for gravitational wave, has detected one such double neutron star system that merge. We knew this would happen and might be detected eventually And because in the first pulsar observed to be in a binary system, it was discovered that the orbit is shrinking over time. So these are data showing essentially kind of like the separation shrinking over time. And this was discovered in the pulsar was discovered in 1974. And then after a couple years of monitoring it, they could tell that actually the orbit was shrinking. So it was the first time that this prediction of relativity could be confirmed, that orbits do shrink over time. And so the people who discovered it, Hulse and Taylor, got the Nobel Prize for Physics in 1993. In the double pulsar, the Earth-Moon separation actually shrinks about 7 millimeters per day, okay? And so in 85 million years, the two of them will plunge and then merge and turn into a black hole. So if you can observe enough galaxies out there, one of these events should take place every couple weeks, and you might be able to detect, which is what we've now managed to achieve. So why do we use these pulsars, which are far away, and why do we use them to test gravity? Because we can test gravity in the solar system. We can send space probes around Mars to Saturn, measure the trajectory, and we can get very good tests of relativity. And here is like the various constraints we can put. So I won't explain that because that's not so easy, and it would take me probably a good 15 minutes to get through. But actually, we can call it the Volkswagen anomaly. So you might remember, not so long ago, this car company, managed to get the tests, for pollution basically working when they were in a lab going at a certain speed under certain conditions, right? But then in real life, actually, the engines would not, pass the pollution tests. Okay, and this was due to the fact that there was a tuning, right, in the software controlling the engine and whatnot, that was basically making it behave in a certain way under certain conditions, and then in a different way under different conditions. So gravity may actually be like that. So basically, if you test gravity when you have low masses and low velocities, like in the solar system, it might just work out and be explained by Einstein's theory, but it could be that when you get to more extreme conditions, it does, this assumption that it should just always be behaving the same way might actually break down, okay? And this is the very idea behind testing gravity, with different types of experiment, where the conditions are different from all of them, because we believe that maybe in one of these experiments it may fail, and then we may learn about completely new physics, okay? And so far, actually, Einstein's theory has worked every single time, so we haven't faulted it yet. But Einstein has been proven wrong, okay? So when people say Einstein was always right, it's not quite true, because, I'm sure one day he probably said, it's impossible to find a good sandwich in this town, and, there might have been a really good sandwich in that town. So the principle of relativity is important, right? So when you make a statement, it depends, with what you compare, the statement you're saying. So for that double pulsar, so far, a colleague of mine, Marco Kramer, has tested relativity to basically 0.05% level precision. And actually, we're working on updates on that, and hopefully soon, there should be some update. But basically, Einstein can be tested to really high accuracy, and it hasn't failed so far. So it's a bit frustrating in a way because we'd like to find it failing somewhere so we can learn new physics, but it hasn't worked so far. Okay, so for the last couple minutes, there's a bonus round actually to my talk. The double pulsar is such an amazing system because, in addition to being such, extreme orbit where you can test gravity and all of that, it turns out that we see the two pulsars orbiting almost perfectly edge-on. Actually, the misalignment of the orbit with our line of sight is about 0.5 degrees. Okay, so it's almost as if someone went there and aligned it perfectly for us. And what happens is actually every orbit one of the two pulsars passes in front of the other one. And as you will see just in a moment in this artistic video, it eclipses the one that's behind. Okay? And it's the first time we can see pulsar eclipses. But in here, it's not the hard surface of the neutron star, the pulsar itself, that creates the eclipse. It's only 10 kilometers across, right, in radius. So it's very small. It's too small. What happens is that around the pulsar, there is the strong magnetic field, and it traps particles. So it traps gas, and it creates what we call it the magnetosphere. So you can think of it as maybe a sort of like atmosphere around pulsars, but very low density and made of particles traveling at crazy speeds. Okay, and this is the gas there that hides the other one behind. Okay, so very fortunate circumstances. So that's what, say, some of the data look like at different frequencies that were observed in radio light. And so the normal luminosity basically would be around unity, and then eventually it drops and then comes back. And the pulsar A disappeared behind pulsar B for about 20 to 30 seconds each orbit. To our amazement, actually, when we took the same data and we looked at a finer time resolution, we actually noticed that there are spikes in the data, but these spikes are not natural noise. So you can see here, this is just like noise. We cannot measure the intensity of light perfectly. But during the eclipse, there are these huge spikes, and you can tell they're at exact distance from one another. So we were mesmerized by this, but also the fact that the distance between them corresponds to the rotational period of the one at the front. So we were like, how can the one in front hide it, and then it kind of like appears all of a sudden, just briefly? So it took a lot of thinking, and eventually a colleague of mine had this great idea. What about spinning a donut? Okay, so that's the spinning donut model. Okay, well, actually, in North America, we quite like donuts that are filled with custard. I know it's not so popular here, but you still have filled donuts, right? But also, some donuts are hollow, right? Have a little hole, and the magnetosphere of a pulsar looks like one of these hollow donuts. So if you were to take one of them and make it spin, but not along the symmetry axis, but you just tilt it and you make it spin, you would reproduce more or less the shape of the gas that's trapped around the pulsar. Okay, so if you do it, and I'll show you a more scientific version of the spinning donut just now, the sound you'll hear is the sound of the pulsar, by the way, the one that disappears. So it should just be a second. Yeah. So you have the pulsar that disappears. We just show a little dot to represent it. And that's the one in front. The pulsar itself is in the middle there. And this old donut, right, is the gas that's trapped by the magnet of the pulsar. And this rod here is the axis along which it spins. But you can see that it doesn't spin about the symmetry axis. So as it rotates, there are windows where basically you can see through because you see the donut sideways. And then there are other times where you see the donut pretty much like face on, and then it blocks anything that's behind. And so with this simple model, we're actually able to reproduce this curve, this light curve that you showed displayed at the bottom. And the real data will appear in just a second in red, and you see that the match between the two is absolutely amazing given how simple this little model is. Okay? And it's a very similar technique actually to reproduce these as what's used in medical imaging for CT scans, so tomography scans. You take pictures from all angles and then you reconstruct what's in the middle. It's quite similar. So using that, we can determine the pulsar orientation in space. And I'll just skip over that. We got data over time. And what we found is that the pulsar is precessing. The spin axis is wobbling like a spinning top. And this phenomenon normally would not happen according to Newton's law. The spin should just remain constant. But it wobbles in this fashion, again, due to relativity. And this is the first time we could actually get a measurement of this effect that was predicted by Einstein. So on a sad note, maybe, well, to finish, but actually it's kind of cool, even though it's a bit sad. The pulsar spin axis is drifting over time. So this cone of light that's been emitted, has now moved up and basically is now missing our line of sight. So the pulsar, we don't see it blinking anymore because we miss the light beam. Okay? So it has disappeared around 2009. But with the modeling, we can actually tell when it will become visible again, and that should be around 2024. So maybe you'll re-invite me for another public lecture in about 6 years' time, and then we'll see if I was correct. So thank you very much for your attention.
Thank you very much. The microphones will be going round, so there will be time for questions. There's a first question here, please.
Thank you very much.
Okay, thank you for that great talk. What is the relationship between the axis along which the light is emitted and the spin axis of the pulsar?
Yeah, actually, we think it's pretty much random. So the light angle and the angle between light and the spin axis can be just anything. There's evidence, well, not clear, but suggestive evidence that the ones that spin very fast, the ones that have been recycling, might have a bit of a preferential alignment, but it's not quite firmly proven yet. So it might have to do with how the matter is accumulated on the surface of those, or maybe just a natural evolution over time. But to first order, it's pretty much random. Yeah, this one.
Thank you. You've given us a lot to think about. Going back to the first chapter in your presentation, Pulsars 101, what are the boundary conditions of a pulsar? Is there a solid surface, if you will? Are they homogeneous? And are they light materials, hydrogen, helium, or are they heavier metals? And how has this process helped us expand our knowledge of what's going on with the pulsar, please?
Yeah, okay. Well, I'll give just a distilled answer because obviously we could spend an entire 4 lectures on this. But the pulsar itself has a hard surface, so it's about 10 to 15 kilometers in radius. Inside the star, most of the composition is neutrons. So neutrons are the building block of atoms. So atoms, the nucleus is made of protons and neutrons, and surrounding it are electrons normally orbiting. In very high density matter, it turns out that electrons tend to merge with protons. It naturally doesn't occur, but at high density it does happen. And when they merge, they turn into a neutral particle, which is the neutron. So inside the star, it's more or less like a soup of neutrons. And again, because of the density, they will tend to form kind of like crystals. And then as you go towards the surface, the fraction of neutronic matter you find becomes lower and lower, and it's kind of like overtaken by more and more like normal matter, if you want. And then we think there's an atmosphere so the crust of pulsars is about probably maybe a couple 100 meters thick. And on the very surface of the crust, there is an atmosphere, which is probably like a centimeter high. Okay? But there is an atmosphere, we think, made, the composition may differ, so it might be hydrogen, helium, or a mixture, or heavier elements even. And actually, in some of them, we know that it's quite carbon or even iron rich, because these stars have manufactured heavy elements over their lifetime. So most likely it's heavy elements. But yeah, so that's sort of like what it looks like. At the very center of neutron stars, we actually have no clue what's in there. There's multiple theories, and the reason we don't know is actually that our understanding of the very laws of physics are actually not able to describe how matter behaves there. So that's one of the hope from studying neutron stars, is that by constraining how big they are, how fast they spin, and whatnot, we can constrain the physics of the object, and then tell which one of the models explain it best, and then it basically tells us, how matter at high density behaves.
Could you explain in outline the mechanism whereby we get a narrow cone of electromagnetic radiation from a pulsar?
Yeah. So the exact mechanism I would actually is unknown. Okay. There's multiple mechanisms and ideas, but no one has really explained it like from start to finish very well. And it's a very active field of research actually at the moment. But the simple picture is that the ionized gas, so the electrified, electrically charged particles are trapped within the magnet of the star, and along the cones here are basically where the field lines don't wrap around to reach the other pole. So we call them the open field lines. And in this region, the gas is not trapped entirely, but rather the particles will spiral along the natural magnet orientation. Okay, they have a sort of like helicoidal motion. And as they move very fast around, spiraling, they naturally emit light through various processes, but basically we know it as synchrotron radiation. And that's the same sort of light that is produced in particle accelerator on Earth. We use them even for like some types of like medical applications. So this light is produced by particles gyrating along there, and basically it produces light essentially in the forward direction of the particle. So if particles are going outward like this, light is produced this way, or this way, and then it makes the light cone beamed in this fashion. So it's probably a combination of the geometry of the magnetic field and how the particles are free to escape, basically, that shapes this cone.
Mine's a simple question.
Yeah, please perhaps wait for the microphone.
I don't need a microphone.
No, but for the record, for the recording, I think
Can you
people.
hear me now? Can you hear me now?
Yeah, thank you.
Mine's a simple question. Is on single pulsars, the angular motion, what you see the spin, what determines that? Is it the galaxy that they're in, or what determines the angle of the magnetic spin, if you like?
Yeah, so it's
the motion.
Yeah, it's completely random. So basically, the star, the axis about which the star spins, and also the axis of the magnet where light is emitted, those are completely random parameters. And in fact, it may be that when the star was a normal star during its regular lifetime, maybe it was spinning, say with an axis that would be upward, say in this room. But when it explodes, we know that actually the star likely gets a kick because the explosion is not perfectly symmetrical. And it usually pushes the star and it starts flying away in sometimes quite large speeds, but also it might make the axis tumble. And so what we observe is that they seem to be random alignments. So it's not... Yeah. So it's not necessarily aligned with the galaxy or anything. It can be anything.
Okay, thank you.
Yeah.
Yes, no.
Are the two beams of the lighthouse the same, or well, are they different rather, or is there some other way to tell whether you're being illuminated by just one beam, or whether you happen to be on axis and getting both beams as something that's rotating at half the rate?
Mm-hmm. That's a good question. So the answer is we don't quite know. So I'm sorry when I have to say I don't know, but at least that's some more things to do for us. So in some cases where you see only one beam like this, we think we're probably intercepting only one of the two cones on one of the two sides and probably close to the center. But then there are cases like here where you see a bit of a horn shape. We think in those it's a narrow cone where basically it's brighter on the outer rim of the cone and inside it's a bit less bright. And so that gives rise to a peak, a shallower region, and then another peak. Then you have some where you have multiple ones. So we think maybe there's like a, concentric cones. But in some cases like this one, there seems to be two poles almost like half a rotation apart. So then it's quite suggestive that, there might be the two, but we're not quite sure. So it's very much, we're trying to understand, and sometimes people come up with various models to try to explain the geometry to determine what it is. And then when you think it works, then they extend the data set to which they try the model, and then there's always a couple ones that just don't behave. So then it makes you wonder, okay, well, do we need another model, or those are different? So we still don't quite know. But the double pulsar, actually, because of its precession, we know so far we've observed one of the two cones. When it comes back in 2024, we'll see that same cone, but actually from the geometry that we can calculate, so this one we have a good grasp on the geometry, we know that if the other beam on the other side is quite similar in opening and such, we should see it at some point, around like the 2030s or so. So we'll see if that one appears at some point, but that would be very interesting to see. Yeah.
Thank you for the talk. About neutron stars, how many pulsars do you think there are out there? I heard your angles and the numbers. Does that inform how many neutron stars we think there might be?
Yeah.
And are there any neutron star black hole pairs?
Yeah. So good question. So actually, indeed, we can only see pulsars blinking due to the fortunate alignment of the spin and magnetic axis alignment. We think that there are probably about only 1 in 10 pulsars that are visible to us that are out there, and that's because the other 9, or 90%, are basically not shining in our direction. So it's about 1 in 10, roughly, we think. Now, as pulsars slow down, also, they're believed to reach a point when it's about 10 or 20 second spin period, where they're not fast enough to generate that process that emits the radio light. And so they basically, it's kind of like the dynamo effect stops working, and then the pulsar is still there, still, spinning, but you just don't see any light being emitted. So there's probably also a large fraction of objects, of neutron stars, that are just not emitting radio light. We don't quite know all the numbers, but we have good estimates based on how much we observe, and also on how many stars explode in our galaxy. So in total, we think with the new generation of radio telescopes, namely the square kilometer array that's been built at the moment, we think we might detect something like 20,000 or so pulsars. And that would be the entire visible population from our galaxy. And then the extent of the full population is probably a factor of 10 larger, if not more. Pulsars, we see them in binaries with regular stars, with white dwarfs, with neutron stars. We haven't detected the one with a black hole yet. So this is what everyone hopes to discover, because they will be quite famous and maybe not a Nobel Prize, but it would be quite an accomplishment. So we're looking for that one. But I think within the next, probably the next 10 or 15 years, especially with the SKA, we should really see most of the population in our galaxy. So we should detect that one. LIGO will detect like these mergers. So LIGO might actually detect a neutron star and a black hole merging. It hasn't detected that yet, but it's expected to do so.
Well, I'm very sorry, but I'll have to bring this to a close now. Otherwise, the Geological Society might charge us extra. Thank you all for coming, and a very big hand to our speaker today. Thank you.